Hey everybody, after doing the lesson today, our first lesson on derivatives, I felt like it went a little bit fast, and so I kind of thought it might be helpful to break this up into three different pieces. I wanted to do one little video on polynomial functions, what happens when you take the derivative of polynomials, and then two separate ones, one on rational equations and one on radical equations. It'll be coming soon, but I wanted to kind of break that up one piece at a time. So what we're going to do is just take a couple looks at a couple of polynomials. So imagine we had these three polynomials right here. H of x is just something like 2/3 x minus 1. G of x was 2x squared plus 7x plus 2. And actually, you know what? I think that's probably sufficient for now. We'll just take a look at those two. So the formal definition of a derivative says that we could take the limit as x approaches 0 of f of x plus h minus f of x all over h. Now keep in mind that f of x is a random point on any curve. So we have some crazy curve like this, and x comma f of x could literally be any point on that curve. And if we move to the right h units, that would be x plus h and f of x plus h. And if we were to connect the dots with those, that would give us our average rate of change. But if we apply this limit right here and we suck h down closer and closer and closer to 0, that would be called our instantaneous rate of change. So how that works, and we have both the alternative version and the formal. I'll go ahead and look at the formal definition first. But when we do that, f of x plus h would look like this following. So all of this is f of x plus h minus f of x itself all over h. Now notice I have not yet put a limit in front of it, which technically means we have the average rate of change. And sometimes we choose to write it this way. So if I look at it, I'd have 2/3 x plus 2/3 h minus 1 minus 2/3 x and a plus 1 all over h. Notice again, I told you I was just looking at the average rate of change, so I'm not bothering to cancel that out. Now I kind of notice that this 2/3 here cancels, and so does the 1. And which is really, really nice because that leads us to the fact that this is 2/3 h over h. So it looks like my answer is 2/3. Now this feels a little bit strange because if I borrow this answer and I say the limit as h goes to 0 of 2/3, well, that would be 2/3. I'm going to pause the video for a second. All right, I'm back. Couldn't stand the song here. Now what's really strange, this says 2/3, the limit as h goes to 0 of 2/3 is 2/3. In other words, h is irrelevant, but the reason for that is it doesn't matter where I'm sitting on this curve. See, there's no x in my final answer, there's no h in my final answer, because it was a line, so of course my rate of change would be 2/3 no matter where I am in the equation. Sometimes people get a little bit freaked out about that when you have lines. Now, if we did the same thing with the secondary function, the limit as h goes to 0 of g of x plus h minus g of x all over h. This is one that we do have to really watch for the little nuances. So again, I'll go ahead and take a look at g of x itself. Here's g of x plus h. So I took 2x squared plus 7x plus 2. So now when I put that in, this is all g of x plus h. A lot of students will forget that when they do all of this work, they still have to remember to subtract the original function back. Now in this case, because it is a parabola, the slope of this curve will be changing over time because parabolas do change. They do not have a constant rate of change. Now, when you take x plus h and square it, this is where a lot of people get themselves into hot water. They forget the 2xh in that original part because x plus h times x plus h is right here. We have 7x plus 7h plus 2. Now in class, we discussed the fact that although this looks really big and scary, if you are very, very careful, wonderful things happen. For example, the 2x squared here and here go away. The 7x here and here go away. The 2's go away. And notice that every single term that is left actually has that h in it. So even though this is a 4xh, when I divide it by that, I would get 4x. I would have a 2h squared, but I divide by h, I'd have 2h. And last, I would have 7. Now, what's kind of neat about that is if someone said, hey, I would like to find the slope from, let's say, 3 to 8, you could use this equation right here because you would literally be saying that you want to pick x to be 3, and h is supposed to be the separation between the two values, which in this case would be 5. So if I took this parabola and I said, hey, what's the slope between the point x equals 3 and x equals 8? I would get 12 plus 10 plus 7. So the slope between those 2 points would be 29. That would be a very, very steep unit of the graph. But if we take it from the average rate of change to the instantaneous rate of change, and I take the limit as h goes to 0 of this answer, because that really was what I was doing in the first place, I get 4x plus 7, which means I can now find the instantaneous rate of change anywhere on the graph. And we like to call this example right here, I actually call this g, not f, so let me do that. We'll call this g prime of x. So if someone were to ever ask you, hey, what is g prime of 2? They're saying, hey, can you use your equation and tell me the slope of g at x equals 2? And you could see right here, 4 times 2 is 8, plus 7 is 15. And so g prime of 2 would be 15. Now, this is all the formal definition of a derivative, which I actually really, really like, but I also am kind of a fan of the alternative version. Not everybody likes it, but I do like it an awful lot. So I thought we'd just maybe look at one problem that is an alternative version of the derivative in the form of a polynomial. So imagine that we had x squared minus 4x plus 7, and I wanted to find the slope at x equals, let's say, 3. So the first thing I would want to know is, what is j of 3? If I plugged in 3, I'd get 9. 9 minus 12 is negative 3, plus 7 is 4. So if I wanted to use the alternative version, I would go the limit as x goes to 3. I want to get really, really close to that value of j of x minus j of 3 over x minus 3. Now what you can still see is if you got really close to the number 3, this still would be 0 over 0, which is the indeterminate form. And I know not everybody likes this version, but if you saw how much work we had to do on the other side of the page, you will see right here, so there's j of x, there's j of 3. If you do it this way, it's pretty amazing how fast the problems become, because we know, based on how they're designed, that they're going to factor really, really nice. This is x minus 3x plus 1 over x minus 3. You would see that these cancel again, and so as x gets very, very close to the number 3, this final answer gets very, very close to the number 4. So again, the nice thing is I didn't have to distribute all those x plus h's and all that kind of stuff. I just could actually plug in the whole equation, and it kind of pops out kind of fast. It actually just takes almost more time writing all of these things as you simplify it down, but you kind of had to do that in the other story as well. So I hope that was helpful to you. That is both the formal definition version with the h's and the alternative definition, which unfortunately is faster, but it's not as powerful because it is limited to only telling you the answer at a particular value. So you should be familiar with both. I hope that helps. All right, have a good one.